Okay, I think we can get started. All of you are almost here. So let me quickly begin with the screen share. Okay, so in the previous class, we have discussed the linear differential equations and the Bernoulli equations. And this was one last question at which we stopped. So has anybody given this a try? Anyone to solve this? Okay, no worries. So let me take it up from here only then. So let's try to solve this first and then move ahead. So the question goes, solve dy by dx is equals to y minus y square minus 2 by 3y, right? So this can be written as dy by dx is equals to 1/3 y minus y square. And if you just rearrange it, dy by dx minus of 1/3 y is equals to minus of y square. Correct? So this is your Bernoulli equation, right? Is this making sense to all of you? Because if you remember, what is the expression of Bernoulli? It was dy by dx plus p into y is equals to q times yn, right? Where p will be a function of x and q will be a function of x. So over here, x is basically 1, but you get the representation, right? All right. So what will be the next step that we'll take? You will divide by y square on both sides, right? So that will become 1 by y square dy by dx minus 1 by 3 1 upon y is equals to minus 1, right? So you divide by y square, correct? And then you'll take your 1 by y square as some z. So that means minus of 1 upon y square dy by dx is equals to dz by dx, correct? So your 1 upon y square dy by dx is equals to minus of dz by dx, right? So if you replace this over here, so this will be minus of dz by dx minus of 1 by 3z is equals to minus 1. So you can get rid of all the minuses. So dz by dx plus 1 by 3z is equals to 1. So this makes your linear differential equation. in Z and X. Okay, is it making sense to all of you up till here? Is it fine? So once we have identified that this is a linear differential equation, so over here your P is basically 1/3 and Q is basically 1. So what will be the integrating factor? Can anyone tell me in this case? Anyone? It will be e raised to the power integration p dx, right? So that is e raised to the power integration 1 by 3 dx, that is e raised to the power x by 3. Okay, and then what we'll do? We'll multiply the differential equation with the integrating factor. So that will be e raised to the power x by 3 into dz by dx plus 1 by 3 times z is equals to e raised to the power x by 3. So that will become d dx of z into the integrating factor is equals to e raised to the power x by 3. Correct? So that means d of z into e raised to the power x by 3 is equals to e raised to the power x by 3 dx, and then you integrate it. So that will become z into e raised to the power x by 3 is equals to e raised to the power x by 3 divided by 1/3 plus c. Okay, and your z is 1 upon y. So 1 upon y e raised to the power x by 3 is equals to 3 times e raised to the power x by 3 plus c. This is your solution. Okay, is this fine with all of you? Any questions? Is the solution making sense? Okay, perfect. So I hope this process is clear to all of you. So for Bernoulli, we'll first transform it into a linear differential equation, and then the same steps that we work out for linear differential equation follows. All right. So with this being discussed, today let's move on to the next type of differential equations that we are going to discuss is known as the exact differential equations. Okay. So before going into this, just wanted to confirm from all of you that are all of you aware of the idea of partial derivatives? Anyone who has isn't sure that how we work out partial derivatives? Anyone on this call?
Sir, it will be better if you explain once.
Okay. So basically, let's say, for example, if you have a multivariate function, okay? So partial derivatives, for example. Okay. Let's say that you have like a function u, which is dependent upon two variables, x and y. So there are basically two independent variables. All right. So this is a multivariate function. And now let's say I want to check that what is the change in u due to change in x. So I'll basically do del u by del x. So this is basically the change in u due to change in x, keeping y constant. Okay. And similarly, if I'm writing del u by del y, it is basically the change in u due to change in y, keeping x constant. All right. So basically, the idea is since you have two independent variables, you want to check the individual impact of these two variables. Okay. And that is where the concept of partial derivatives come in. Now, how we are going to work them out? So just like the way we calculate the derivatives, the process of calculating the partial derivatives is also exactly the same. Okay, everything that we know about differentiation, the chain rules, the formulas, the product rules, and all those things are applicable here as well. Okay, so the rules of differentiation apply to partial derivatives as well. Okay, nothing much changes over here. It is just that you will have a function now of two variables and you need to treat one as constant when you're doing partial derivative with respect to a variable. All right. Let's say, for example, if I take something like this, your u of x comma y is equals to, let's say, x square plus y cube plus xy plus y times, for example, log x. Okay. So can anyone take a quick guess what will be del u by del x?
2x plus y plus y by x.
2x plus y plus y by x. Absolutely. Okay, is it making sense? So when you're differentiating with respect to x, y is to be treated as a constant. All right. And similarly, what will be your del u by del y?
Sir, why the y cube is not there?
Because it is to be treated as a constant, right? The derivative of a constant is zero. So
Oh,
the y cube will
oh,
disappear. Okay.
So is that 3y square plus x plus log
All right.
x?
3y square plus x plus log x. Perfect. Yes. Okay. This is correct. Okay. Any questions, anyone? Please feel free to ask me if there is anything that is not clear over here. All right. repeating it once more. When you are partially differentiating with respect to x, you will be treating y as a constant, just like you do in differentiation. And when you are doing the partial derivative with respect to y, you need to treat x as a constant. Okay. And this logic is basically what you extend if you have more than two variables as well. If you have, for example, x, y, z, then there can be three possible partial derivatives. And in each case, you will, if you are differentiating with respect to x, partial derivative with respect to x will be computed by considering y and z as constant and so on. All right. So this logic can be generalized further, but we need not go further, at least now, because for differential equations, we are only considered with the relationship between two variables. Okay, to start with. All right, is it fine with all of you? How to calculate the partial derivatives? Is it making sense? Any questions on this? Anyone? Okay, perfect. So now let me come back to the idea that I was trying to explain, the exact differential equations. All right. So let me just write down two statements for you all to just note them and then we'll start. Let's say that you have a differential equation in this form, where m is a function of x comma y and n is also a function of x comma y. All right. I request you all to take a closer look at this, the structure of the differential equation that I am writing. Okay. So this is a differential equation which you are writing it in the form m times dx plus n times dy is equals to 0. All right, where m can be a function of x and y and n can also be a function of x and y. All right. So the idea says that a differential equation like this star is said to be exact if del m by del y is equals to del n by del x. Okay, the partial derivatives. So if you are representing your differential equation in this format, m dx plus n dy is equals to 0, and the partial derivative of m with respect to y is equals to the partial derivative of n with respect to x, then such a differential equation will be called as a exact differential equation. Okay, noted everyone? All right. So after representing the differential equation in m dx plus n dy equals to 0 format, we need to check if the partial derivatives are equal or not. That will basically confirm that your differential equation is exact or not. All right. So let's say that, let me just begin with a small example. Suppose I give you a question like this. Yeah. X square y plus 1 times dx plus y by 2 plus x cubed by 3 times dy is equals to 0. Check if the differential equation is exact. Okay. So can anyone tell me, looking at this differential equation, what is my m over here and what is my n?
M is x square y plus 1 and n is y by 2 plus x cube by 3.
Correct. And in order to check if this is exact or not, what do I need to calculate? I need to check for del m by del y, and I need to check for del n by del x. So can anyone quickly work this out?
Sir, both are same, x square.
X square. Others, are you getting the same answer?
Yes, sir.
Okay. So that means in this case, since both the partial derivatives are equal, so we can conclude that the differential equation is exact. Right? Correct? Taking one more question. Suppose you have something like y dx minus x dy is equals to 0, where your both x and y are positive. Okay, I want to check if the differential equation is exact. So in this case, your m is y and your n is x. Correct? So what are the partial derivatives? Sorry, this will be minus x.
0.
0.
1 হবে
কোনটা?
মানে ফার্স্টের পার্সিয়াল ডেরিভেটিভটা 1 হবে, সেকেন্ডেরটা 1 হবে। না
Minus
মাইনাস
1.
আছে না, 1 আর মাইনাস।
Right?
Sorry, 1 or minus 1.
1 or minus 1. So, okay, others, are we getting this?
Yes, sir.
Yes, sir.
Okay. So over here, the partial derivatives are not matching. That means my differential equation is not exact. Correct? Okay. Now suppose, so this equation is not exact, right? Now suppose if I ask you to do something like this, that transform this equation, that means this original equation, such that it becomes exact. Okay. Now let me just elaborate a little bit more on this. What do I mean by transform? All right. Now suppose, okay, let me start like this. So if I ask you that I have my original differential equation, right? And I multiply that by, let's say, 1 by x square. Okay. So what is the differential equation that I get if I do this? Can anyone tell me? So you have your original differential equation and multiply it with 1 by x square. What do we get if I do this? Anyone? What's the equation looking like if I do this?
y by x square dy dx minus 1 by x dy is equals to 0.
So this one, right? So if you try to check if this is exact, so over here, what is your m? Y by x square, and your n is minus of 1 upon x. So what is your del m by del y?
One by x square.
Correct. And your del n by del x?
What are 1 by x square?
So what are we seeing? That in this case, your del m by del y is equals to del n by del x. So that means if you multiply the differential equation with 1 by x squared, it is becoming exact, right?
স্যার
Take a
বলছি
look at one
এক্সাক্ট
more.
ট্রান্সফরমেশন তো অনেক ভাবে এক্সাক্ট
হ্যাঁ,
ট্রান্সফরমেশন তো অনেক ভাবে হতে পারে ওয়ান বাই এক্স ওয়াই দিয়ে মাল্টিপ্লাই করে দিলে তো হয়ে যাবে ডেরিভেটিভ দুটো জিরো
হ্যাঁ,
হয়ে
হ্যাঁ,
যাবে
একদম. Exactly, exactly. There is no unique way to do this. There are multiple ways. Okay, take one more example. For instance, instead of 1 by x square, if I multiply with 1 by y square. So what's the differential equation if I do it in this way? Yes, anyone? What's the differential equation looking like if I do this?
1 by y dx minus x by y square dy.
And if I try to check for exactness, over here your m is 1 upon y, your n is minus 2 by y square. Sorry, not 2, x by y square. So your del m by del y is minus of 1 by y square, and your del n by del x is also minus 1 upon y square. So here also your del n by del y is equals to del n by del x, giving you an exact differential equation. Okay. And likewise, like Avik has also already pointed out, you can also try that. That if you multiply with 1 by xy as well, then also you get an exact differential equation. So what are we essentially doing? We are trying to multiply our differential equation with a function such that it becomes exact, right? And that function with which you are multiplying to make the differential equation exact is known as the integrating factor. Okay. We have already discussed this terminology, but over here it means a little different, right? So in this case, in the case of an exact differential equation, the function with which I am multiplying the original differential equation to make it exact is what is known as the integrating factor. All right. And obviously, when I'm calling it the integrating factor, obviously it has got something to do with finally integrating the function, right? It will help in integrating the function. We'll come to that later. But for the timing, as you can understand, that the function or the factor with which I am multiplying the differential equation so that it becomes exact is known as a differential equation. Sorry, integrating factor, right? And as you can see that the integrating factor is not like unique. It can be multiple possible ways to construct the integrating factor. Like in the first example, what it is just a function of x, right? And in the second case, it is a function of y. And you all can try this out. Let me put this as a homework. That if you consider your integrating factor as 1 upon xy, which is essentially a function of x and y together, then also you can check if the differential equation will turn out exact. Okay, so that means your integrating factor for a differential equation is not unique. Okay, a very, very important point to remember. All right, there can be multiple ways to construct an exact differential equation out of an equation which is not exact. And as you all can maybe guess, that obviously it's on convenience. कौन सा ज़्यादा easily हो जाएगा. That is the kind of integrating factor that we usually prefer to take. Okay, you can take a function of x as an integrating factor, a function of y, or a combination of both. Whichever works best for you, you can proceed with that to make the differential equation exact. Okay, is it making sense to all of you? Any questions? Okay. Now, obviously, this differential equation was pretty simple, right? Y dx minus x dy equals to 0. So it is like, I believe to many of you, it might sound like a guesswork. We need to guess a function that we need to consider as an integrating factor, right? So what happens if you have a little bit more complicated functions or something where guess is a little difficult task, right? So let's say, for example, let me discuss it through a question. Suppose if I give you a question like this. Okay. First of all, can anyone check and tell me if it is exact?
Yes, sir.
Exact. Okay. So over here, what is your m? X into sine y. And your n is x plus 1 into cos y. So del m by del y will be x into derivative of sine, which is cos, and del n by del x will be cos y treated as a constant. So just not exact.
না স্যার, হ্যাঁ এক্সাক্ট হচ্ছে না।
Not exact, right?
Sorry, sir, not
Right?
exact.
Correct. Okay, others? It's coming out not exact. Okay. Now suppose if I ask you that can we think of an integrating factor to make this differential equation exact? Obviously, it might be a little tricky, right? So let's begin with the idea. Now, as we saw, that integrating factor may not be unique, right? You can take it in any manner, all right? To start, let's say obviously function of x या function of y लेने से the calculation looks relatively simpler. So let's say that I choose my integrating factor to be some function of x. Whatever it is, we don't know what it is as of now, but some function of x. All right. And what is the outcome of considering an integrating factor? It is such a function that after I multiply with the differential equation, that means when I do integrating factor times the differential equation, which will look like fx into x into sine y dx plus fx into x plus 1 cos y dy is equals to 0. So over here, this is your m, and let's say I call it m dash, and this is your n, right? N dash. So integrating factor is such a function such that after multiplying it with the differential equation, it becomes exact, right? Do you all agree with this? After multiplying the differential equation with fx, this condition must hold. Del m dash by del y is equals to del n dash by del x. Correct? That is the function that we want to find out. I want holds. You agree? So now try to work these partial derivatives. What is my del m dash by del y? And what is my del n dash by del x? Yes, anyone? So m dash is fx into x into sine x, right? So if you differentiate it with respect to y, x's will be treated as a constant. So fx into x will be there, derivative of sine y will become cos y. Okay, and over here cos y will be treated as a constant, and this will follow product rule. So second x plus 1 into derivative of first, which is f dash x, plus first into derivative of second, which is just fx. Okay, so that means fx into x into cos y is equals to cos y into x plus 1 f dash x plus fx. Okay, so using this equation, I need to find out my fx. Okay, so if we start to work this out, your cos y's will cancel out, so you'll have fx into x is equals to x plus 1 f dash x plus fx, right? So that means your x minus 1 into fx is x plus 1 into f dash x. So I can write this as x minus 1 by x plus 1 is equals to f dash x by fx, right? And we can integrate both sides. All right. So can anyone tell me how we should work out the RHS? Anyone?
Log of mod fx.
Yes. So this will be just log of mod fx. And what about the left side? How to work that out?
X minus log of mod x plus 1 এর হোল স্কয়ার।
কি করে বার করলে একবার এক্সপ্লেন করো।
মানে উপরে যে x মাইনাস 1টা আছে সেটাকে x প্লাস 1 মাইনাস দিয়ে করে অ্যাডজাস্ট করে দিতে হবে, মাইনাস তাহলে হয়ে যাবে x প্লাস 1 মাইনাস 2
এইটা
x
রাইট?
প্লাস 1 মাইনাস 2 করলে তার হ্যাঁ মাইনাস 2 করলে এটা তাহলে
So this will become x minus 2 times log mod x plus 1 is equals to log of mod fx plus c. Correct? So I can write this as some log c, that's fine. So your x will be log mod fx into x plus 1 whole square times c. So e to the power x is equals to fx into x plus 1 whole square into c. So your fx is okay. So this is your integrating factor if you are constructing a function of x. All right. If you multiply the differential equation with this, then the resultant differential equation will become exact. Okay. You could have started with a function of y as well, or a function of xy. All right. So you would have reached a different functional form, but eventually, when you multiply that with the differential equation, the result will be that your equation will be exact. Okay. Is it understood by all of you? So given any differential equation, you can actually work out the integrating factor. Okay, by starting off with a function of x or function of y, by using the condition that after you multiply the differential equation with the integrating factor, the equation has to become exact. So we use that condition to obtain our fx in this case. Okay. Understood, everyone? Any questions? All right. Now, obviously, this can be done for all the differential equations, but for some particular kind of differential equations with certain characteristics, there are certain rules that you can apply directly to get to the integrating factor. All right. So that is where we will begin our discussion on the next class, which is the rules of finding out some integrating factors. Okay. So obviously for any differential equation, you can work out and get to the answer, but there are some handy rules that come in for some particular kind of differential equations that we'll discuss in the next class, for which you can straight away apply the rules and get the integrating factor without going through this series of calculations. All right. So that is our topic for next class. So that's it for today's class. All of you, thank you everyone for joining. I'll request you all to maybe just revise this idea of exactness once more, so that if there are any questions, we can take that up first in the next class, and then I'll proceed with the rule. All right. So thank you everyone for joining. See you all in the next class. See you all can disconnect. Thank you.
Thank you, sir.
Thank you, sir.